you are known as one of the most successful initiators of the largest physics experiment ever, which is taking place in the Large Hadron Collider. And I was wondering, when you decided to build the Large Hadron Collider, were you already sure that you were going to confirm the existence of the Higgs particle?
No, we were not sure.
Uh-huh.
But the whole idea was with the Large Hadron Collider to build a machine and then also experiments which could give a definite answer whether it exists or not.
Mm-hmm.
But well, there were many indications that this theory must be correct, but we were by far not sure that it exists.
Good. How would you explain the Higgs particle?
Well, maybe I have to take here a little bit more time in
Yes.
the sense of telling you that the Higgs particle, the Higgs boson, is actually a manifestation of the theory which predicts that there would be a so-called scalar field which is present everywhere. The vacuum is not empty, it's actually filled by this famous Braut-Englert Higgs field, and by exciting this field with the energy which is available at the Large Hadron Collider, one can, for a very short time, create a resonance, a particle, which immediately decays again into other particles. Now, the Higgs field is very fundamental because it is responsible for the fact that the other elementary particles actually do have a mass. They acquire a mass by their interaction with this Higgs field. And from that point of view, it was one of the very important, outstanding questions in physics: why do elementary particles have a mass? So that's and the Higgs field is so to speak the smoking gun verification that there is really that this field exists.
Mm-hmm. Good, thank you. During the experiment, people were often speculating that you were looking for the Holy Grail. And then in 2012, you made this spectacular discovery of particle decay consistent with the Higgs particle. And can you tell us, what does the discovery mean for particle physics in general?
Well, it means really that it was the last missing piece in the framework of what we call the standard model for particle physics. The standard model of particle physics gives us a very nice, consistent description of all the fundamental processes of matter, which consists of three families of matter particles, they are called quarks and leptons, and of the particles which are responsible for transmitting the forces, the bosons. And there are, in the standard model of particle physics, there are the three forces: the strong nuclear force, then the electromagnetic force, and the weak force, which are unified, described by that. Mm-hmm. Not described by the standard model is gravitation. We may come to that later. Mm-hmm. So the standard model is beautiful but not complete. There are things missing. Now, the Higgs particle was really, the Higgs boson was the last missing piece in this picture, and it's maybe because of that sometimes people thought that this is such a fundamental ingredient, and indeed it is. I mean, it's a fantastic thing if you think that some 50 years ago, a few eminent theorists had a very abstract idea how actually all these elementary particles do get a mass. Some are massless, some have a very large mass. That's why it's often also called symmetry breaking, spontaneous symmetry breaking, and that in the course of the years, all the ingredients of this picture of the standard model have been found, all the matter particles, the gauge particles, which mediate the forces, and then it was just this last piece which was missing, which is the Higgs boson. So in that sense, it was somehow the crowning culmination for the standard model of particles.
And this discovery, what future research does it inspire?
Well, I have already mentioned that actually there are many phenomena which are not described or explained by the standard model of particle physics. So one knows that there must be something beyond the standard model. Some theory which, of course, would include the standard model because it has been verified experimentally so well, but which would give us some explanation, for example, for one of the greatest mysteries in general in physics is the so-called dark matter. We know that actually the matter which acts gravitationally, this may be most familiar of the four forces, however not described in the standard model, we know that there is matter which acts gravitationally, for example in the dynamics of galaxies, and there must be more of such matter, actually 4 or 5 times more of this matter than what we see in the stars, which are visible. And that, hence the name dark matter comes from that. This was for the first time observed and then deduced in the 1930s already, actually by a Swiss physicist Fritz Zwicky. And then in the 70s there was an American astronomer, Vera Rubin. She made calculation of the speed of stars in the arms of these beautiful galaxies, spiral galaxies which we see, and the rotational speed was not explainable by the mass again in the visible stars. So there is something beyond the standard model. Another mystery is that we actually only see matter, and we don't see some primordial antimatter. All the galaxies are matter, not antimatter. Naively, one would expect that as much antimatter was produced in the Big Bang as matter. So that's another thing which we study. Maybe I want to say also something which is important to note. We always, of course, connect the Higgs boson in this indirect way through the field, as I said, through the question of mass. But we should be precise and say this is the mass of the elementary particle. It's not the large part of the mass which we observe in the daily life. In public lectures I always say it's only about 800 grams, which has to do with the Rout-Englund-Higgs mechanism, because it describes about 1% or even a bit less of the mass. The other part of the mass comes from the energy binding strongly together the quarks and gluons which build the protons and the neutrons, which then at the end build us.
The Atlas group was mentioned in the jury statement for the Nobel Prize in Physics last year, and this is a huge distinction. I was wondering, your research will probably not end here. And I was wondering, what is the next particle that you're going to look for?
Yeah. So you're absolutely right. This is only the beginning of the journey, of course. And just to give you also an idea, at the LHC we have accumulated only about 1% of the total number of collisions which we will examine. And actually next year we will also start with an energy which is higher, so we can make more massive particles following the famous formula of Einstein that energy is the equivalent of mass times c squared. Now, first of all, we have to verify and study very much whether this Higgs boson is really the standard model Higgs boson, where there would be only one, or there are extended theories which predict more than one Higgs particle, and also predict some properties which will be slightly different from the one which we observe. Mm-hmm. We have not measured this with sufficient precision yet, because we need more data to verify that. So one line of research with the Atlas experiment at the Large Hadron Collider is to measure with much higher precision the Higgs boson. But even much more exciting is really to look for indications of this physics beyond the standard model. One very elegant and popular theory is called supersymmetry. This theory actually would have a candidate particle for the dark matter. And it could well be that with more energy now in the LHC, we would actually produce this dark matter particle. So that would be really even a more giant step if we would find it. So this is a typical road to other investigations. Then there are investigations like, well, we assume that the quarks, electrons, they are the elementary particle, but maybe there is something, maybe they are also composed by a new hypothetical super strong interaction which binds some prions, sometimes they are called, and they build together the quark. This will be a little bit repeating the history when one went, well, first from atoms to the nuclei, then the nuclei, finally the quarks and gluons, but maybe there is yet a deeper underlying structure. And such phenomena could eventually show up at the LHC at high energy. So there are many such directions one is searching for.
How much bigger should the Large Hadron Collider be for the next discovery?
Well, so the Large Hadron Collider will restart now next year at the full design energy, and it will be exploited for something like 20 years or so. Now, it is true that we are also already start dreaming, maybe more than dreaming, maybe investigating what would it mean to build a machine which is really essentially an order of magnitude more energy. That could be, for example, a ring which is 100 kilometers in circumference, the LHC is 27 kilometers, but then one would also have higher field magnets, so one could contain in this racetrack higher energy particles, even protons, which, if we would have collisions at 100 TeV compared to 13, 14, what we will have next year, of course you can really produce much heavier particles. You do, again, a big step into the unknown.
Mhm.
This is music for the future, as we say, but people are investigating this. This would be for 2045 or something like that. Not for me, but maybe the children of my children would still see this working. We have started with the LHC in 1984, so it took 30 years to get to this stage. So it's not so absurd to think in timescales of 2045. So.
As the leader of the Atlas project, you invited Slovenian physicists to collaborate with you, and they have been working on this project for 20 years. I was wondering, how would you evaluate the knowledge of Slovenian physicists?
Well, first of all, that was indeed during the time when I was the spokesperson, the project leader, which I stopped to be in 2009, but over a very long time I had the privilege really to bring this collaboration together. I can say that this was a very fruitful collaboration with the Slovenian groups from the Stefan Josef Institute and the University. As you say, this started about 20 years ago, and at that time we were still developing the technology detectors. There's a lot of local, my colleagues here had a lot of expertise in semiconductor detectors, also electronics. Then we also had a very fruitful collaboration with industry, with high-tech industry, making specific parts which were not easy to build for this detector. But everything went very well, and so in the meantime, then also, of course, in the beginning there were only few physicists involved. I mean, of course, always Professor Marko Mikuš, who is the leader of the Slovenian Atlas team. But with the time, more people joined, and a lot of young people also. So it's a very pleasant collaboration. And for me, it was always nice to come back during this period from time to time, see the progress. Clearly, also. It's nice and to see that it stimulates a lot of interest in the country for science. And I was this was on Wednesday evening, I gave a public lecture in the framework of the Novi Gorici University, and there were a lot of young people, very enthusiastic, interested, so I think that's good.
What will future bring to the Atlas experiment and the Slovenian group within it?
Well, of course, I don't have a crystal ball, but I'm sure that there's still a lot of physics to come, and there is, of course, a great hope that there will be further discoveries. I always use as a little comparison with the Higgs boson. We had a very concrete goal that we wanted to find it, and it is very nice that actually within 3 years of operation, we already could make this and announce this discovery. So in a way, one could say it's like, for example, in figure skating and sport, there is a program where the skaters have to do some imposed figures. And then, however, there is the whole second part, which is the free skating, free discovery maybe, and so there's still a lot, there can be a lot to come. Nobody can guarantee that. That's the essence of basic research, that one cannot be sure that we find something, but the hopes are very high. And the instrument and the accelerator are working to an extent that we can really have these hopes very strongly.
What are the challenges of building a bigger collider?
Well, there are of course different categories of challenges. There is, first of all, a technical challenge, namely one would like to put in this bigger ring stronger magnets, so one has to develop the technology of very high field magnets. So this is a big development in terms of technology. Of course, a very, very big challenge for engineers, special engineers and so on. So that's one thing. A big challenge is also to build such a big tunnel. It's a civil engineering challenge, if you want. Again, one can be confident that this can be solved. Then there are, of course, also big political challenges and challenges to bring the financing for such a machine. Clearly, this needs a very long-term commitment from governments in CERN, in the organization, also from countries which are not from Europe or which participate. As physicists, of course, the community have really to agree, like it was for the LHC, that this is the machine we want. We cannot have everybody his or her individual wishes. We would have to pool all our resources. Resources in this, now I was talking about the money in a way, but of course also intellectually, because it will be already the building of Atlas was a difficult task, and the building of an experiment for a future collider will be also very difficult. And I mentioned that, of course, one needs also big challenges, the support from the government. And of course, in that context, I would like to talk about the Slovenian admission, which is still pending to CERN as a member state. And I hope I express this all the time, that this really will happen. This would be such a natural thing. Of course, the Slovenian physicists are at the forefront, like any other European or Western or Japanese scientists. It's almost unnatural that Slovenia is not a member state of CERN. And that was one of the topics I had the privilege to discuss with the President of Slovenia in my visit in January this year. So I hope this will soon happen.
Science today seems to be focusing more and more on applied research and solving practical problems, which means that private companies invest money in research and then they want immediate results and they want profit. What do you think about this?
Well, of course it is understandable, but one must also realize that the basic research, like what we do at CERN in the LHC, is stimulating and spearheading, in a way, a lot of development which then are used in applied research. This is both true for the technologies, but actually is also very important for the people which are educated. I mean, of course, not all the students which make their thesis or so, or the young engineers which work on the LHC, the machine, or the experiments, they can stay in the research sector, but they learn to solve problems which are needed. This knowledge is needed later on in private industry, and so I think the applied research would very quickly miss a lot of resources if there is not also this fundamental research which has no bounds. I mean, clearly applied research has to be very bounded in new ideas, cannot always flourish as much as in fundamental research. So I think both in a way need to go together. We also, on the other hand, in the basic research for our instruments, of course, we rely heavily on excellent collaboration with applied, with industry, high-tech industry, and so on. So they go both together.
My last question. How much energy is hiding in all these particles inside the atom? And can we expect that one day, inside the atom, we will find the energy to travel to the other end of the universe?
No, I don't think this is the case. This is a bit science fiction or so. But again, of course, to use peacefully energy, which particularly nuclear energy or so, is a big issue, and I think the solution we all know the solution cannot be just by dogmatically ignoring it. The solution must be in very wisely mastering these type of energies, and that's my personal view on this point. Of course, we should exploit as much as possible all what we call the green energies, but if it's wisely done, I think also energies contained in the nucleus, that's really what in a foreseeable future one can talk about. It's also energy from the nature, so, but it's a very serious, deep question, of course. But travel to other galaxies or so, that is very, very futuristic.